Hey Mark, how are you?
Oh, hello. I'm fine. How are you?
Pretty good. I saw your email. Um, I'm thinking about it. So
Oh,
give
okay.
me a few days.
Oh, thank you. Okay. Good. I'm glad you received the email.
Yep.
I wanted to make sure it's good you got it because I wasn't sure if it was David Dot Ratchkoff at Thrace Systems or just David at Thrace Systems, but see, I
Both go
had it right.
both go the same place.
Oh, they do. Okay, good.
Yeah, Google allows for unlimited aliases,
Oh, I see. Okay.
so they both go the same place. It's okay. About
Hi, David. Hi, Mark. This is Bala.
Yeah, hello.
Hello. Hi, good morning, guys.
maybe we'll give everyone a minute extra, and then we'll get started.
Okay.
Okay, why don't we get going? If anyone else joins us, they'll catch up to us. And if anybody missed it, you can follow on the recording. Um, Before we get to the test stuff, does anybody have any opens updates that they would like to share? Um, Maybe Mark, anything on your side that you want to share before we
Uh,
get started?
I'll just share that the last time I shared something, I shared about transient analysis and the
Yes.
discussions about whether that's necessary for the early feasibility analysis for 3D blocks. Um, I just wanted to mention that other things that are happening or being discussed for 3D blocks. One is there's a discussion about making it easier to supply a bump map file because a lot of times your bump maps might have a lot of regularity in them, like a repeating pattern. And so there's an enhancement proposal for the bump map to enable you to have a more concise text because you're taking advantage of those repeating patterns instead of having to explicitly state the location and connectivity and such of every particular bump. Um, and in addition, from Siemens, there is a proposal to enable um, arbitrary rotations instead of just fixed 90-degree rotations. And they say they have customers that are actually using that. There's been a fair amount of discussion, and some members were pushing back on that, saying, why in the world would you want to do that? But they have customers that are using that, and so they're requesting that as an enhancement for 3D blocks.
Hmm,
So anyway,
okay.
that's some things that are going on in that work group.
Who proposed the concise description of bump maps?
Uh, I forgot the name. I need to get back to you on the name of the person who's proposing that, but I'll get that to you.
Okay. Yeah, that's a weird one because this is already done in JEP 30. It seems like people are just copying from. CDX and get ready and put it into 3D block. So um, I'm not sure um, uh, what the point is, right? Uh,
Okay. Yeah, that'll be interesting. I'll check if the person is aware of the JEP 30 standard then. I didn't know that myself. But
yeah,
okay.
yeah. Job 30, specifically Michael Durkin, spent a lot of time in optimizing the bump maps where they can support millions of bumps.
Okay.
So um, you know, that's been done. I know people like smaller files, but at the end of the day, it's the same thing, right? So yeah,
Uh,
okay,
so that's a good point. I'll raise that to the person who's making the proposal, and I'll get you his name.
yeah, yeah. Because apart from that, Jeb 30 is right. It's not just a hey, here's a bump map, right? And some bumps and names. It has a long list of attributes that gets added to each bump, right? Electrical attributes, is it power, ground, signal, what kind of signal is it, right? And a whole bunch of attributes can be defined on those pumps, which are very, very useful.
Okay.
So if 3D Blocks is going that route, maybe they should, right? Right, are duplicating standards, right? And descriptions. And that's a bad thing to do in general,
Mm-hmm.
right?
Yeah, I agree with you. They shouldn't be trying to create something new if there's a standard there already.
Yeah, and I guess in some cases, right, um, standards may diverge where one standard wants to go in that direction, the other wants to go in the other direction, right? And maybe that makes sense. But in this case, uh, my feeling is that this looks like more like convergence, right? Both are trying to solve the same issues, right? And that sounds like convergence to me, and trying to solve it in the same way, right?
Mhm.
It's the same solution to the same problem. So um, it's good idea to kind of maintain one standard and improve on that instead of diluting two standards, right? And getting into pointless divergence of standards, right?
Yeah, good point. Okay.
Okay, hey, Josh. All right, thank you, Mark. Let's get started with the um, test design kit. Continue on the description on the discussion we
Hi,
had
David.
uh, before. Bala, do you remember we covered? Uh, do you remember what where we ended last time? Did uh,
Um,
did we cover the power and voltages or not yet?
no, the power and voltages, yeah, we covered that.
Oh, we covered power and voltages.
Yes,
Okay. All right, then let's take a look. Then we have two more tables left. One is the for parametric tests, and the other one is for PAT standards.
right.
Okay. Let's see. Okay, let's. Okay. Why don't you walk us through the parametric testing?
Okay, so the parametric test, which is predominantly used through the boundary scan kind of applications, so where the people do characterize the pads, like so this is mainly done at the qualification level, and whenever there is a new technology node and it comes up, and then they across the test chips they try to read out the there are four major tests that they do in terms of the voltage testing, like VOH and VOL and VIH and VAL. So these are the um, level spec is being provided from the pad design. So in the post silicon, they try to achieve the same the parameters like through applying the boundary scan test, where through the boundary scan structures they try to write the transitions to happen, and this is mainly to cover the slew rate and then the stable state values of this the pad outputs and the inputs, and so also to measure um, how that the transients are captured, right? So to make sure that this unspar with a spec to detect the transitions, and so that because that is a dictator for the pad characterization, and also this will be used to um, provide the different internal RC delays controllability, like the pads also comes with lots of configurable registers where we can vary this internal RC delays and then achieve this performance boost with a different delay network, right? So in very often we also get into the the production test like the DFT as well, where for example TDO, which is not giving up the proper transients, and across the binning it gives some issues, right? So that's where people go and check that the TDO for like what is the VOH VOL, and how that transient affect, and they try to do this the cycle binning efforts through the ATE's test method. And so this is,
Okay, so
yeah, this
so
is
let
more
me.
of an automation effort for it will help from the translating these parametric values from the models, and then to help with characterization test program generation.
Okay, so let me understand. Uh, Let me repeat what I understood, and correct me if I'm wrong. The way I understand this information to apply would be first during generating the test patterns. You would expect that the IO libraries which you have to provide you information about the VOH and VOL and VIH and VIL, right?
Right,
And you use that information from the libraries to develop the test,
right,
right? Basically, that's the first step. Then the test is developed, and the silicon is out. The patch will get will get uh, uh, characterized, and in that case, after the characterization, you're gonna get your final values for VOA view the voltage high, voltage low values on input and output.
right,
And you would give those values, those final values, to your customer.
right, right. That will go in a data sheet.
Okay. Those.
So right now the um, the chiplet vendors, they will provide these data sheets with what type of pads and the technology and the parametric values, and so that will be used by the test engineers to create the patterns, and there are so like a boundary scan test equipments which can utilize these values and generate the patterns, and there is a full automated equipments are available, but these the values that which comes from the data sheet, it's a manual process, so the CDXML can help to drive that, right? Where
Yeah.
yes, these data are already available as part of the spice simulation models and things like that. And so any pad vendors and who has the regression, and they will have these values, right? From those regression data only they get these values and put it in the data sheet,
Yeah.
right?
So, yeah, let's take a step back. Say, when I'm I'm the chiplet owner, right? And I'm generating my tests based on the IO libraries, right? So that I can the test pattern, so that I can give it to the test to manufacturing, right?
Mm-hmm.
Now, do you expect? Actually, let me ask you a question like this: do IO libraries already provide some of this information, or this is again in a data sheet that people read? In other words, is that flow where I actually own the silicon and I'm providing the chiplet to somebody, but when I own the silicon and I'm doing the generation of test patterns, is that flow fully automated, or you would expect, or there's still some manual work that you would expect CDXML to automate?
Okay, so the BSTL, like the BST test pattern generation, like there are a number of tools like they are available in the market. So the entire process, like generating the pattern on the fly, applying on the hardware, and checking the result, and then regenerating the patterns. So it's all end-to-end, thoroughly automated today. But then these spec levels, which has to be feed uh, into that emulator or hardware setup, is manual, right? So we need to have, yeah, if you want to like fully automate this, right? Because people sometimes, I have faced this type of problems also, like in Intel, like where whenever there is the transition happened from the one product to the other product, right? So people overlook this type of values, right? Where they will think that at the end of the internal, like the test engineers, they think that okay, so before I was using the a test program from the, let's say, Granite Rapids, and then there is a Sierra Forest, there is another server chips comes, and then but both are coming from two different technology. So one is from the Intel 7 and another is from the Intel 5 or Intel 3, right? So then people overlook they take that test program as it is and then try to put the new patterns on top of it and then retest it, right? Which is everything is going to pass because it's a relaxed voltage level, which is for the 5 nanometer technology to 3 nanometer technology. There is a delta values, right? So somebody has to manually review it and make sure that the latest data sheet from the new product captures the updated value, and then that is what it's used for test qualification, right? So because of these manual errors, like that could be overlooked. That's what my point is, like. So this adding these 4 additional parameters as a placeholder in the CDXML, so that will help mitigating these type of problems.
Okay,
Right. The
so
CDXML tool, like whoever is going to deploy this into the CDXML, this CDXML method, so they will have an access to the pad qualification regression database, and they can on the fly query that and apply it here, and also pass it on to the test program development.
okay, yeah, I guess my question is, uh, right, when I think about this, there are two personas in this whole scheme, right? Um,
Mhm.
the one of the personas is the end user of the chiplet, right?
Right.
That they
Right.
need to know what the parameters are for the pads, right? And today
Right.
they read that from a paper data sheet, and
Right.
what we want to do is put that in a file that can be automatically read in by the test instruction flow, right? Basically, skip the manual part. Okay. The second persona is basically what happens internally within the chiplet owner. All right. What I'm trying to understand is the way I see it is there are two steps, right? One is actually I'm trying to understand the application of CDXML within an internal flow. Would CDXML still apply where whoever generated the test patterns gives that initial data sheet to somebody that then they run say the manufacturing would characterize the part and update that data sheet? Is that the expected flow, or really this is purely manufacturing takes this test pattern, takes the chip, tests it, and creates the data sheet at that point? How do you see the application of CDXML?
Okay, the data sheet is one thing, right? Where people normally takes that from the paired regression. Then they take the value and then put it in the data sheet, and there could be multiple data sheet. There is a product data sheet, and there is a manufacturing data sheet, right? And then there is a characterization data sheets, right? So different people uses it for different purposes. But the point is like, how do we avoid like manual errors, right? Or copy paste error, or people forget to update that values based on the from the product to the product.
Yes. Yeah.
Right. So that's a caveat. Like, yes, today if you look at like, for example, any people who are like who are doing like a, for example, SIPA analysis, like they will get these values from the model by itself, right? So there will be PDPX models, like they will have this all these values inherited from the design by itself, right? But then do we know those models are going to be utilized for the test program generation? No, right? Yes, none of these test program generation tools are relying on those type of complex models to extract the values and check that results, right? Whether that is really matching with I mean, that is whether it is utilized for the test program automation or not, right? But having this type of intermediate language, which will help the EDA development into that direction, where when we open up this CDXML with these parameters, so they know like who's the persona who they have to talk, and then how to extract that values.
Okay. Say that that last sentence I think was important. Can you say
Yeah.
it? Oh,
So what I mean is like, so the any pre-silicon development workflows, right? Across the different personas, like let's say there is an RTL integrator or there is a layout integrator, so they will have their own models to play around with this, right? So simulation model will have this certain set of assertions, and so they will have some hard-coded values, and that so the RTL integrator guys can do some validation for that. And similarly, for the layout guys, they will have their own PTPX models, so they can do all the timing checks and the signal or power integrity checks with that, right? But where we see the gap is like when it goes to the pre-silicon to the post-silicon testing, that's where the gap is, like where it's only the information is carried through the email or in the data sheet, right?
okay.
And then
So let's talk for a moment about the pre-silicon pre-silicon test, right? Where you do the test development.
right.
You have whoever when that persona is developing that test, they are going to have inputs from libraries, right?
Right.
Do you expect them to generate this kind of model for the out of basically whoever does pre-silicon test development, they run test pattern generation, things like that. And as part of that, one of the outputs is this kind of a table that says, here's the paths and here's their voltages.
Okay, no. In the pre-silicon, we don't apply these different voltage levels, right? There is no concept of minimum output level or maximum output level like
Okay,
VOL or VOH, right? So
right.
it's all
Okay.
zeros and ones in the pre-silicon. So they from the SOC validation or the even the DFT validation, they don't get to check this. Like all they do is I'm forcing one and I'm able to shift that value to the from the capture and then shift it to the TDO and then I'm able to read that one value or not, right? It's just a forcing zero and strobing zero and through the TDO and forcing one on the pin and then strobing the one on the TDO, right? It's just that checking that the capture and the shift operation through the tap controller across the board scan cells. Is it that baby step validation is done correctly or not at the pre-silicon level? But only the pad characterization they can do this, right? Where when they do, people does the um, spice with the models, like they do this type of extensive test, like where as part of their pre-silicon characterization. Right, so the pre-silicon characterization, like that's the only place where they will have these type of models and with assessments, all the capabilities for their regression qualification when they run um, um, any type of spice level validation.
Okay. So pre-silicon, when pre-silicon characterization is performed, which the way I understand it from you is it's just simulation based, right? Do
Right.
you expect that step to output this table?
Okay, so I think Rajesh has raised some hands. Rajesh, you have some inputs to share here?
Yeah. So can you hear me,
Yes.
David?
Yeah. Go ahead, Richard.
Yeah. So actually, yeah, Bala very well explained. Thing is, I think um, we are coming from, just to give the more perspective what David was looking for. We are coming from structural test perspective, especially from DFT point of view, what Bala was saying, right? So all these boundary scan tests will just check connectivity and all that. So voltage levels we do not check in our test, whatever that from the BSDL as an input, and it can is all automation. But I think the only test from BSDL which can come close to what voltage is like a clamp or IZ, which is like it actually tri-states all the IOs. Okay, so that is the only thing. But as far as these voltage levels are concerned, 2.64 and 0.66, I think that should be coming from the characterization test, which falls under functional domain. So I'm not sure the output, because I've not seen it, how they test it. But they need to, of course, pre-silicon before the chip tapes out, they need to somehow validate these, right? Somehow. And that is, I think, mostly is coming from libraries, pad libraries, are coming from the given vendors if you are not in-house. So that's, I think, to answer your question, David.
Yeah, I guess I'm pretty sure I'm not asking the right question because I don't understand
No.
this.
Every question is good because
Uh,
when
yeah,
I'm other
yeah,
side of this thing, right? Pre-characterized.
yeah.
I've not seen it
Right.
checking voltage
W- w-
levels.
what I'm trying to understand is this, right? I got the part where post-silicon characterization will have this table generated, right? Which will be based off of the actual measured voltages, right? Right?
Right.
Okay. My question is that the actual post-silicon testing, does it need a table like this with inputs, what voltages they should be targeting? right? Where say, right, I'm the post-silicon test person, right?
Yes, for
And
the
right, I'm expected to generate this table. I can generate that table, right? I can run the test and generate it. But do I need input table like this that tells me, hey, here is your starting point, test with this, and whatever you measure at the end, that would be the final result. But do I need this an input table like this, which we made maybe based on simulation, on libraries, or something like that?
I believe this is correct understanding, David, according to me. Yeah, we'll need that input toward the PSV team, post-silicon validation.
Okay, so who will generate that table then for me? Whom do I go to get that initial table?
so that is from the data sheet, right?
Correct. I think
So the pad level data sheet, like so normally how it works, like it is primarily the characterization team. They work with the pad designers and get these numbers, and then they run through the test and then see in the post silicon level correlation, and then they give it's kind of a iterative process where if we find any delta differences, and then they go back and tighten the space models like
Okay,
and the
okay,
root cause the analysis,
okay.
right?
So there is
And
here's what I understand that. Since you mentioned datasheet and we want to replace datasheet with CDXML, then in that case, the way the flow would be is whoever does the test insertion and generation of test patterns would need to generate a CDXML that is basically a design level datasheet, right? It's still not the final product datasheet. It's just internal to the chiplet owner, where whoever did the test insertion, they deliver patterns, and they deliver a CDXML that says, hey, based on off of the pad libraries, here is the voltage values that we gathered, right? Then
right,
me as a post-silicon characterization person, I get a CDXML, right? And a bunch of test patterns. So I can run my characterization using that data sheet, run the patterns, and see if things match or do not,
right,
right? And
right.
I can I would I can update the data sheet with the final post-silicon measured values and ship that, or I can go back to the whoever inserted the test and tell them, hey, you know what, this is so far off, you need to take a look at this, right?
Yes, right.
Okay. Is this
Yeah.
the
So
flow that you were thinking of?
yes, right. And the characterization test is results are the final, right? Where that will tell us how accurate the space models are, and if there is any deviations, so they will close it with like enhancing the space models and to match with the silicon results, or the vice versa.
Yeah.
So and then this finalized results, which will be also used for the protection test program development also, right, where they have to um, uh, use that the reference voltage levels for the stopping, and as well as for the driving for the inputs, they should go with the planned levels for in the final protection screen.
hey, Bala,
Yes.
uh, can I ask a question?
Mm-hmm.
Yeah, so this you see basically your point was the gap between pre-silicon test and the transfer of data to the post-silicon. That is where you are finding gap, right?
Right.
Maybe to your Intel experience, but I mean we have been. I mean Intel. Just one example. All big chip manufacturers are now chiplet manufacturers will have this problem, right?
Right.
Qualcomm, Broadcom, everybody is going through that post-silicon validation is like without that you cannot. So far, uh, what do you see CDX ML going to play a role in what just having a data instead of in a text file, just automation. That's what you are saying. You're
Right, right. Yes, these are the cases where or when we enter this ATE support model, right, as a DFT people, so we get questions from the different test engineering teams, like where characterization teams or the production teams. So how they will qualify these voltage levels, and from where who is the contact person they from to go person, like to get that initial setup ready, and then who will do a sign off, right?
no. I
So
think my question was not about the person involved. And my question was data exchange. I think that is what the value CDXML is bringing. But so far, what I'm seeing, your point is instead of getting everything in a Excel spreadsheet and pre-silicon team after the tape out will update that spreadsheet and the people from post-silicon team will read that spreadsheet like that. Instead of that, you want to use CDXML.
right, right. Yes, this becomes a official LRM kind of stuff, right? Where people who newly joins a test engineering group or a correction group, they don't have to be dictated through another meeting or a walkthrough session, right? They will have everything here, and as long as they can get this CDXML data populated, and they will know like everything that they have everything what they need.
Yeah, I understand, but thing is, I think the power of CDXML is portability, right? David, you can basically put more light on this. If you have different vendors, chiplets, and all that stuff, that's what just one consistent uh, standard across chiplet. That's what CDXML was developed. But
Right.
right now, characterization is basically, let's say it's beyond this DFT domain. Just characterization is a separate team who does a lot of things which you already mentioned, right? Spice simulation. So
Right, right.
far, how come, I mean, just thinking aloud here, how come this need is come not so far? Because chiplet or chips doesn't matter. Because now we are not talking about chiplet problem. We are talking about even the inside chip design house, the data uh, going from pre-silicon to post-silicon. So, but maybe open question. I'm thinking how it was not a problem so many years.
Oh, okay. So right now, yeah, all the major like companies, right? For example, Qualcomm, like they have everything in-house design. They have
Yeah.
IO designers, and they have their characterization owners, and they have a
Yes.
test chip.
Yes.
Like so all these team, as long as they are in-house and they don't have any restriction of data exchange, right? So
Correct.
imagine
Correct. Correct.
the OSATs, like they have to go through this pain.
Okay. Now it makes sense because Qualcomm I actually worked with. They have very fantastic internal tools, so you will not see that outside.
Right, right.
Okay. Okay. Thanks.
Yep.
So yeah, that's where my concern is, like because most of these scenarios, like it comes as a surprise to the DFT people also, because DFT people does not prepare these type of inputs and supply with their test patterns, right? And so it's mainly the characterization team. They will go after who are the pad designers and the pad library owners, and they will get the data sheets from them. So most of these informations are sprinkled across different data sheets also, and so that's where my next table comes in, like where the 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 characterization guy needs to be told that for a particular chip what family of IO standards that he has it across the pins, right? And so each um, so once he knows the comprehensive list of the pad technologies, like so he might have a simple GPIO or complex high-speed IO, and with varying technologies node also, right? Based on the needs. Um, so once he has that the broader picture, like so how many different technology nodes that he has it, then it is easy for him to strip down that groups of pads pertaining to those families, and then come up with this the complex data values, and create the subgroups of programs, per each for each standard or family of that pads.
Yeah. So Bala, let me ask you a question. Would it be, I'm thinking, all right, what if I had a table like this that says, here is this IO, here's this IO, right? Here's the IO type.
Mm-hmm.
Here is, let me copy the right tree. Here is this guy, right?
Mm-hmm.
And then I take these values and say like this, right? And then
Right.
for this guy, I can do like this, right? So basically, I describe each IO type, right? Because these are going to be very small number of different IOs, right?
Right.
Basically describe each IO. Maybe here I can have additionally input output, or actually this could be input. How about like this, hypothetically, and this is just output, right?
Mm.
Yeah, obviously this is single-ended, right? If it just says input
Right.
single-ended, but maybe, or maybe this would need to be known whether it's input output, right?
Right.
So okay, we can refine this a little later, but
Mm-hmm.
basically have the IO type, describe the parameters of each IOs,
Mm-hmm.
right? And then come into each signal and say, hey, here is this signal here. This right, this signal here, this is the IO that drives it, right? Just
Right.
do a simple mapping like that.
Right.
This is kind of what you had in mind overall, right?
Exactly. Yeah. So this is the bare minimal knowledge the test engineer needs to have, right, to get to 100% of the parametric test coverage,
Yeah,
and how properly he can articulate the level spec from the data sheet,
right.
right?
Okay. Yeah.
So based on that level of knowledge, then he should be able to fairly generate the patterns and then run through it. Yes, I had really difficult time during my Intel experience. So yes, these test engineers are not consistent. Like they will go from domain to domain, jump like blindly run through it, and then give you back the result, right? So if you are a DFT guy, like without
Yeah.
having this thorough knowledge of the level spec and the standards, like a regular DFT guy will not have this level of deep understanding, right? He will say like, okay, as long as the test is passing, okay, we are good. Like, so he
Yeah.
doesn't worry about whether the test is doing its intended task or not, right? So that is what my concern is today.
Yes. Yep. Understood.
Yeah, and Tony is a very well advocate of this, right? So he doesn't like
Yep.
the PDF data sheet. Like he wants to see um, uh, interoperability of the tools and the exchange of the data through the models.
Yes.
And so that's where I think we must, I think, consider these examples bare minimum, and
Yep.
then put as a placeholder, right? So that
Yeah.
the test development folks, for them, for their paranoia checks, like so this can give more inputs, and if they are overlooking few cases here and there, and but if they have more cases than this, and they can also come back to us like, okay, can you expand
Yeah.
additional scenarios, right, like this, right?
Yes.
So
Yes.
yes, otherwise CDXML can go as another language LRM kind of stuff. Nobody notice it, right, without the
Yeah.
proper
That's
explanation
right.
on the intention of this effort.
That's right.
And one more scenario I'm foreseeing now. See, we are Bala and me, right? We are talking from DFT perspective. But the tests are functional test also. There's all characterization. They also fall under functional test. So you need to also run through some person who does develop functional tests, not just structure DFT tests. Because
Right.
same problem will
Right.
arise
Yeah.
there, because if they are not the characterization expert, they will ask the same questions that we are asking.
Right.
Yes.
Right. Yeah. 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 Functional power management guys thermal guys, reliability guys. Yeah, there are a number
Yeah,
of guys can
yeah,
tailgate us at this.
yeah. No, I think overall there's a lot of value in understanding the voltages on these ions, right?
Right.
Apart from operation, that as Bala mentioned, power thermal, even right functional testing, yeah, understanding what how this was characterized, what the values are. I think that's going to be valuable, right? So I don't waste my time in um, testing with IO values that are outside of the supported by the silicon, right?
Right. Right.
It all falls into place. I wanted to ask you, Bala, about, so I get this part, this is easy, the single-ended ones. Explain to me the on the differential IOs, um, how
Okay. So the differential IOs again it is goes into the more of a functional category where the way the IO trimming are done, and so there are lots of data coming from the pre-silicon spice simulation kind of efforts, right? So I'm not an expert at that, but I just gathered some data sheets and try to articulate these numbers here. But beyond the numbers, I don't have background working knowledge on this, right? So we need some expert from the high speed IO, the people who really work on the trimming and have that the IO boot up uh, uh, kind of a test case bring up, right? So those people will be able to chime in more specific scenarios here. So yes, um, within the trimming itself, they have lots of um, the how they lock the differential pads, things like that, right? So there are many things are involved there. So it is I don't think we'll be able to automate that part, um, but this is the minimal ask that we can ask from the CDXML standpoint, right? From the what the differential pad guys are giving us in the data sheets in terms of the parametric characterization for those individual pads.
right? Uh, are you thinking about this uh, specifically as it applies to the differential pair, or are you thinking also as well as the single-ended IOs in UCAE, for example, right? There's some which are single-ended, some which are differential, right? Uh, I- would you apply this kind of values to the data bits to the data pins, for example, or basically the entirety of UCE falls into this?
Um, so that I need to work a little bit harder. Like I don't have like a straightforward answer on top of my head. Maybe I can dig through that question and need to read out some different data sheets and compare. So we can maybe have a follow-up session next in the next call.
Yeah, okay. Yeah,
Yeah,
I think
sure.
that this is important and not important. Well, it's important and interesting, right? Because
Mhm.
this would a lot of the pins today on a chiplet are going to
Mhm.
be high speed, right? UCAE data bits, UCAE clock. You're going to have HBM pins, right? The GPIOs of this kind of like these two are going to be very few, right? So
Right, right,
uh, uh, I'm really right. I think it's going to be valuable if we are able to capture a lot of the IOs in this scheme,
right.
right?
Yeah.
I guess this would apply to SerDes pins if we need to declare anything on those. I don't know.
Mm-hmm.
Um, because yeah, let's take SerDes for example, right? Uh,
Mm-hmm.
would I give VOA, VOH, VOL to my customer, right? Say I have a chip today, right? Would I give them
Mhm.
VOH, VOL? I don't know, or I'll just give them the register, which is for the trim settings. And then when they put it into their system, they can play with that in their firmware and figure out what works, right? From my point of
Right.
view, I have characterized my service to PCIe Gen 6. I
Mhm.
have the silicon, and I tell my customer, hey, I have characterized it, and here's the trim register.
Right. Yeah, I think the high speed IO and so within that, as you articulated, like what is the difference between the single-ended and the differential, and so there are many things that we can create as a CDXML input. Again, because there is no unique method for testing these, right? The test methodology is part of their IP design today. Right. So the what are the implementations does support for the testing, and so that's where they dictate um, the uh, the nature of this thing, right? So the yeah, again from the electrical parametric test, it's again everything is given in the data sheet, and I need to refer few other data
Yeah,
sheets, see
yeah,
how what it makes sense for us, right? So we do not want to blow up the CDXML and give all the permutation combination, right? So the bare minimal stuff, if we provide, so that gives a fair the, the base definition of this CDXML for that particular
right,
type of test. But people can always extend the attributes and create more and more um, parameters, right? Custom parameters that then they can
right,
extend it.
right. But let me. Here's a little bit of a different context that I'm thinking.
Mhm.
So I bought a chiplet A from one vendor, and I bought chiplet B from another vendor, right? And both have UCAEs.
Mhm.
Okay, I get for the GPIOs, I get the voltage values, VOH, VOL, and when I look at it, I can see, okay, these two chiplets, they're going to be compatible when I set up the GPIOs voltages like that, and it's all going to work, right?
Mhm.
What do I need to know for UCAEs? Is it
Yeah.
just, does it go, right? Remember, in the SIPI kit, we are looking to add the eye diagrams and openings and things like that, right?
Right.
Would that do it?
Um, yeah, I'm not sure about it. There's more of an integration question that you're asking, right? So here we are
Yeah,
talking about
but
test by the
say
pad.
I also need to develop the test for this part that includes these two chiplets, right?
Right, right.
What do I need to know, right? And one vendor gave me their chiplet, the other vendor gave me their chiplet. I need to stitch them together, right?
Right.
Again, I'm the testing session guy. What do I need to know about the UCAEs? Is there basically an implicit assumption that it, in a way, it's kind of similar to SerDes, right? If I get two chips today
Right, right.
with SerDes, all I
Okay,
need
so
to look.
yeah, if you're talking about just the die-to-die interconnectivity test for the UCIe, like so, there are a number of methodologies there, right? So LFSR based and ATPG based. Like there are many cases, many scenarios are there, but that is mainly to cover the die-to-die any bridging fault or the stucket fault, transition fault, those type of typical fault model related testing, right? But that I don't think in that sense like we are doing any electrical level of test there. So it's more of a like a interconnect test. Like I believe. So your question is like mostly um, we can get an answer from the people who run the SIPA kind of analysis with the PTPX models
Yeah,
across this the um, package integration tools,
yeah. I
right?
think in terms of electrical testing of the UCAEs, The way I'm thinking is explicit testing and implicit testing, right? If I'm
Mhm.
developing my own chiplet with UCAE, I'll have to do explicit tests on that UCAE interface, right? But once I've tested it and it's good, and now I'm at the level when I'm integrating those chiplets, is the electrical, I would think that the electrical testing is actually implicit.
Right, right. So
Right.
once you
I
made
can,
an interconnect, then you don't have an option of like doing a isolation testing, right? So you have to
that's right.
follow through the loopback test and then bypass one phi and then to go to the next phi, do kind of like jumping around different phis and try to correlate. Right,
Right.
that's the
But
only option
yeah,
at the interconnect level we have it. So,
right. But
so I don't
that,
think the CDXML is going to solve any problems there. Like so,
yeah, exactly.
CDXML, yeah, is mainly the just the file which is getting exposed out of the package. That's where we can play a role between the test program development and to bridge the gap for these level settings.
Yeah. Okay. Yeah, that would that kind of goes towards my thinking that these VOH VOL are probably gonna come in uh, somewhere built into the the interface testing itself, right? Meaning I developed
Right,
my I have my silicon chiplet, I test it. That test will cover the electricals of the UCE, and once it's out the door, that UCE becomes a kind of standard. It's black box, right? I get another chiplet, I just connect them together. I really don't have to worry about necessarily the electricals of the silicon itself, right? Then the tests are going to cover any connectivity, stuck at faults, and so on, right? Opens and so on,
right,
but not necessarily look at. Uh, I might look at eye diagrams, but really what I'm looking at eye diagrams is the integrated product, whether it meets the bit error rate.
Mhm.
Okay, I think we should dig in a little bit more into this. Kind of the reason I say this is twofold, right? Uh, Again, as I said, there's so many pins that are going to be HBM and die to dies and so on one hand. On the other hand, we are going to have some pins which are going to be going outside of the package, like a whole bunch of SerDes and maybe LPDDR pins, stuff like that, right? Is there, right? So my question for you to look at is, what does test creation, not test generation need in terms of description of those pins which go outside of the package, right? Because again, they're going to be
Right,
sitting, right? Do we need to describe those in some special way for test purposes, right?
right, right.
And then
Yes.
maybe specifically when it's inside the package, all the die-to-dies, HBMs, UCAEs, balls, or whatever the die-to-die interfaces are there. Do we need to describe anything about those? And specifically thinking about the high-speed pins, right? Not necessarily about these guys, right? The GPIO type pins, right? These are, I think we have those covered. But specifically for the high-speed ones, is there any additional information that test creation needs? I think that would be super useful.
Yeah,
Yeah,
I think, yeah, let me take an action item like so. Maybe we should compare a couple of data sheets and then we can
yeah,
have some more readouts
right.
to give some more solidification information on this, right?
Yeah, I think okay. So here's the good news. I think you're lucky because next that's that meeting falls on Thanksgiving.
Mhm.
So obviously we are not going to have meeting on Thanksgiving. So you have a month to look into that. Would that be enough time for you to take a look and give us
Yeah,
some feedback?
yeah, I have UCE spec, like I'm trying to find some other I mean, alpha wave UCE spec we have an access.
Okay.
So I like also see is there any other UCE spec is there, like so that way within the UCIe, like across two different vendors, like what they are recommending, right? So we can have some readouts, and also I'll see if I have some access to any of the SerDes kind of files.
Yeah.
Right, so we can compare across two generations of files, like how it is, right? PCIe or whatever it is. So I think some level of comparative study, I think, will give us some explanation of what are the test needs for these files, right?
Yes. Yep. Exactly.
So yeah, we don't have to be like 100% solution oriented. Like as long as we
That's
give
right.
some the base information, and then create some sense of those test requirements, and there's a dependency for the test program development and the DFT and test engineers, right? Um, so that is, I think that itself is a big win-win for everybody.
Yes. Yep. I agree. Okay. Yeah. Let's see. So I canceled the meeting on Thanksgiving. You probably saw me
Okay.
doing that. So we'll then reconvene the week after that, which is November the 41st. Today is the 13th plus 28 days. That would make it November 41st, right? Which is 11th, December 11th.
Mhm.
Okay, so we'll reconvene then on December the 11th and cover these final ones. And we'll hash out, we would have covered this table by then.
Okay, sounds
Right.
good.
All right. All right, everyone. Any last thoughts and comments?
No, thank you.
All right. Next week is an SIPI kit discussion. If you're not participating in that, happy holidays, and I'll see you on the 11th with Test Kit. Otherwise, I'll see you next week for SIPI.
Okay, sounds good.
Bye-bye.
Okay, thank you, guys.
Thank
All
you.
right, everyone. Thank you.
Thank you.
Okay.
Bye.
Okay.
Bye.
Bye.